Welcome to Presidency Senior Secondary School online class. So today we continue our 8th lecture on Unit 2, that is solution. So in last class we have discussed Raoult's law and numericals from Raoult's law. So one more numericals for you for your homework. So first of all, write this question. Very important one. This is also from Raoult's law. So this numerical is exactly same as first numerical. So vapor pressure of chloroform CHCl3 and dichloromethane formula CH2Cl2 at 298 Kelvin are 200 mm mercury and 400 mm of mercury respectively. Number 1, calculate vapor pressure prepared by mixing 25.5 gram of chloroform and 40 gram of dichloromethane at 298 Kelvin, and also mole fraction of each component in vapor phase. So these two values are vapor pressure of chloroform. So this is vapor pressure of chloroform and this is vapor pressure of dichloromethane in pure state. Okay? And these are mass of chloroform. Mass of chloroform, and this one mass of dichloromethane. So if we divide mass with molar mass, then we get number of moles of chloroform, and if we divide 40 by molar mass of dichloromethane, which is obtained from formula, then we get number of moles of dichloromethane, and then sum up both this, then we get total number of moles, and if number is divided by total number, then we get mole fraction of chloroform, and 1 minus mole fraction of chloroform equal to mole fraction of dichloromethane. So this is our first part. So next, so first of all, find out mole fraction of chloroform. What is mole fraction of chloroform? Number of moles of chloroform divided by number of moles of chloroform by number of moles of dichloromethane. Now what is number of moles of chloroform? Its mass divided by molar mass. What is molar mass of CaCl3? Carbon 12, hydrogen 1, 3 chlorine, 3 into 35.5. So this is molar mass of chloroform. So if we put this number here, then we get number of moles of chloroform. Similarly, number of moles of dichloromethane, mass equal to 40 gram divided by molar mass of dichloromethane. What is molar mass of dichloromethane? Carbon 12, 2 hydrogen, 2 into 1, 2 chlorine, 2 into 35.5. So if we put here, then we get number of moles of dichloromethane. Now if we put number of moles of chloroform here, number of moles of chloroform and number of moles of dichloromethane, then ultimately we get mole fraction of chloroform. Here 1 minus mole fraction of chloroform equal to mole fraction of dichloromethane. And then use this formula. Partial pressure of chloroform equal to mole fraction of chloroform into, so mole fraction of chloroform obtained from this relation, and this is our PC naught. Then we get partial pressure of chloroform. Similarly, partial pressure of dichloromethane equal to mole fraction of dichloromethane into vapor pressure in pure state. So 1 minus mole fraction of chloroform, we get XD, and this is our PD naught. Then we get PD, and if we sum up this, then we get vapor pressure of solution. So this is our vapor pressure of solution. So first of all, find out number of moles, then mole fraction of chloroform, then mole fraction of dichloromethane. Now from Raoult's law, if we put mole fraction of chloroform and mole fraction and vapor pressure of pure chloroform, then we get partial vapor pressure of chloroform. Similarly, if we put here mole fraction of dichloromethane and vapor pressure of pure dichloromethane, we get partial pressure of dichloromethane. And if we sum up both of these, then we get answer of this, which is total vapor pressure of solution. So this is our first one, number 1. Then we consider vapor pressure in mole fraction in vapor phase. So again use Dalton's law of partial pressure, which is used in our first relation or first question. What is Dalton's law of partial pressure? Partial pressure equal to mole fraction into total pressure. So by using this relation, we get mole fraction of both component in vapor phase, as in previous first question. actually vapor pressure of solution, we have already discussed this one. Vapor pressure of liquid in liquid. Already discussed this one in last class. That is, which is under Raoult's law. Today we will consider this one. Vapor pressure of non-volatile solid in liquid. So today we will consider vapor pressure of non-volatile solid in liquid. First one already discussed, which is so next we consider this one already discussed. Today we will consider this one. Vapor pressure of non-volatile solid in liquid. Example of such case, say glucose in water, say sucrose in water, say urea in water. So all these are example of non-volatile solid in liquid. So these are non-volatile solid and these are liquid. So now we consider solid in liquid, solid in liquid, solid in liquid, and of course solid are non-volatile. Now if we consider, say this is any liquid, say water, and here some solid which is non-volatile, say glucose. So glucose in water, so solid in liquid. So when only water is present, then it is called pure solvent, and let P naught represent vapor pressure of pure solvent, which is generally denoted by A. Now when glucose is dissolved in water, so now it becomes solution. When glucose is dissolved in water, now it becomes solution. And if P represent vapor pressure of solution, then PA naught, that is vapor pressure of pure solvent, is always greater than P, is always greater than vapor pressure of solution. So always vapor pressure of pure solvent higher than vapor pressure of solution. It is PA naught means vapor pressure of pure solvent always higher than vapor pressure of solution. Now why vapor pressure of pure solvent higher than vapor pressure of solution? So there are two reasons why vapor pressure of pure solvent higher than vapor pressure of solution. There are two reasons. If we consider pure solvent, say water, so entire container containing water molecule, we know that, so these are water molecule or solvent molecule, and we know that vaporization is a surface phenomenon. So entire surface is occupied by water molecule. So vaporization takes place. Say its vapor pressure is P naught. Now if some solid is added to the water molecule, so here a homogeneous mixture is obtained. Here is homogeneous mixture is obtained where both solvent and solute are present. So here white one represent water and black one represent solid. So in previous case, that is when only water molecule present or only solvent molecule present, then entire surface is available for vaporization because entire surface is occupied by water molecule. Now when some solid is added which represent black dot, so some surface area occupied by water molecule, solid sugar molecule. So surface area is less than previous one. So as surface area decreases, rate of vaporization also decreases. So vapor pressure of solution is less. So this is one reason why vapor pressure of solution lower than vapor pressure of pure solvent. There is another reason. If we consider pure water, only water molecule, then only water or liquid interaction takes place. And if some solid is added in water, then here now solid liquid interaction takes place. In case of pure solvent, only solvent interaction or only liquid interaction. When some solid is added to form a homogeneous mixture or solution, so here solid solvent interaction takes place after mixing. And we know that solid solvent interaction or solid liquid interaction is stronger than liquid interaction. So now more intermolecular bonds, so less tendency to escape out from the solution. So lower will be the vapor pressure of solution. So there are two reasons why vapor pressure of solution less than vapor pressure of pure solvent. Number one, in case of pure solvent, entire surface is occupied by water molecule. When some solid is added, some surface area occupied by solid molecule, so surface area less. So less surface area means less vaporization. So lower will be the value of vapor pressure. This is one reason why vapor pressure of pure solution lower than pure solvent. And second reason, in case of pure solvent, only liquid interaction. In case of solution, solid liquid interaction. And magnitude of solid liquid interaction is more than liquid interaction. So more interaction, so less tendency to escape out from the solution. So lower will be the value of vapor pressure. So vapor pressure of solution lower than pure solvent because of two reasons. Number one, less surface area available in pure solvent, in solution, and number two, more solid liquid interaction in solution. So it is clear that vapor pressure of pure solvent is always higher than vapor pressure of solution. Now we consider in this case also another Raoult's law. Another Raoult's law in case of non-volatile solid in liquid. So there is another Raoult's law. So previous Raoult's law for liquid in liquid, now solid in liquid, and solid is non-volatile. Now if we consider say previous one, that is this one. So this is liquid A and this is liquid B, and both are mixed together to form solution where both A and B are present. So we get two relations from this Raoult's law. P1 equal to XA, PA0, and PP equal to XB, PB0. Now this one is liquid and this one is solid. In previous case both are liquid, now this one is solid. So when this one is solid, B is solid and which is non-volatile, so this case is not possible here. This case is not possible here. So simple reason, because here now B is solid and it is non-volatile, so there is no tendency for B to get vaporized from the solution. So second case does not arise. So we consider only first case. Now since only liquid is A here and B is solid, so this one is actually vapor pressure of A in liquid, that is partial vapor pressure, now represent vapor pressure of solution. Vapor pressure of solution, and this one represent vapor pressure of pure solvent, and this one represent vapor pressure of mole fraction of solvent. Mole fraction of solvent. So here relation PA can be replaced since it represents solution. So PA can be replaced by simply P equal to XA PA0. So in this relation, P represents vapor pressure of solution, PA0 vapor pressure of pure solvent, and XA represent mole fraction of pure solvent. Now, for a particular temperature or at constant temperature, vapor pressure of pure solvent is always fixed. So at constant temperature or a fixed temperature, vapor pressure of pure solvent is always fixed, means it is constant. So if we remove constant, then we get P proportional to XA, because here P represent vapor pressure of solution, PA0 represent vapor pressure of pure solvent, and XA represent mole fraction of pure solvent. Now since mole fraction of pure solvent at a particular temperature is always fixed, so PA0 is a constant. It is a constant value for a particular solvent at a particular temperature. So if we withdraw constant, then we can put proportionality symbol, so P proportional to XA. So here we can define Raoult's law. What is Raoult's law? At constant temperature, vapor pressure of solution of solid in non-volatile liquid is proportional to mole fraction of the solvent. Is proportional to mole fraction of the solvent. Again, so in this case another Raoult's law. What is Raoult's law? Vapor pressure of a solution at a particular temperature is proportional to mole fraction of the solvent. So this is Raoult's law for non-volatile solid in liquid. Raoult's law for non-volatile solid in liquid. So Raoult's law may be stated as at a given temperature the vapor pressure of a solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. So this is another form of Raoult's law. So mathematical expression is P equal to XA P naught. So this is our mathematical relation which is obtained from this one. P, it is vapor pressure of solution, P naught vapor pressure of pure solvent, and XA represent mole fraction of the solvent. So next our important topics, Raoult's law as a special case of Henry's law. Raoult's law is a special case of Henry's law. Now, if we compare Raoult's law and Henry's law, then according to Raoult's law, P equal to XA PA naught. We have already discussed. And according to Henry's law, also discussed, P equal to KH. So this is mathematical form of Henry's law. So here partial pressure, here also partial pressure, here also mole fraction of solvent, here also mole fraction of the solvent. So if we compare both these laws, then only difference is PA naught and KH. Now what is PA naught? PA naught represent vapor pressure of pure solvent, which is a constant quantity at a particular temperature. And from Henry's law, KH is called Henry's constant. So only difference is one contain partial pressure, mole fraction, Henry's constant and vapor pressure of pure solvent, and both are constant. So KH is a general constant. KH is a general constant, and PA naught is a specific constant. Thus, Raoult's law is a special case of Henry's law. So same. So these are different. So if two are same, then KH may be equal to PA naught, which is a special case. So next we consider what are similarities and dissimilarities or difference between Raoult's law and Henry's law. So next we consider similarity and difference of number 1, both the law applicable for non-volatile solid in liquid. Second one, in both those laws, vapor pressure is proportional to mole fraction of the solvent. Only difference is proportionality constant. In Raoult's law, proportionality constant is P0, and in Henry's law, Kh. P0 is constant, and in Henry's law, Kh is constant. So these are similarities and difference between Raoult's law and Henry's law. So next we consider Raoult's law, numericals from Raoult's law, that is solid in liquid. That is our second case. We have already done first case. So here, first of all, the right question. An aqueous solution of glucose is made by dissolving 10 gram of glucose having formula C6H12O6 in 90 gram of water at 303 Kelvin. If the vapor pressure of pure water at 303 Kelvin with 32.8 mm mercury, what would be the vapor pressure of solution? So here glucose is solid, water is liquid. So this is case of solid in liquid. So for solid in liquid, our relation is P equal to XA PA naught. So in this case, P equal to XA means mole fraction of the solvent, which is water, equal to vapor pressure of water. Now, mole fraction of water equal to number of moles of water divided by number of moles of water plus number of moles of glucose. Now, what is number of moles of water? Mass of water is 90 gram. So, this is mass of water. So, mass of water is 90 gram. And molar mass of water is 18. So this is number of moles. So again number of moles of water 90 by 18. And number of moles of glucose. Mass of glucose is 10. The molar mass of glucose we all know 180. So 90 by 18. 90 plus 1 by 18. So which is equal to 90 by 91. So P equal to vapor pressure of solution equal to 90 by 91 into PA means vapor pressure of water, which is equal to 32.8. So our answer is 32.44 mm of mercury. So again here glucose in water. Glucose is solid, water is liquid. So this is case of solid in liquid. So here we use this relation. It is Raoult's law second form. Now we require mole fraction of water. What is mole fraction of water? Number of moles of water divided by total number of moles of water. What is number of moles of water? Mass of water 19, molar mass of water 18. So again number of moles of water 19 by 18. Number of moles of glucose. Mass of glucose is 10 gram and molar mass of glucose we all know 180. So finally 90 by 91 mole fraction of water. So mole fraction of water 90 by 91 and mole fraction of pure water is 32.8. If we multiply, then we get value of 32.44 in our mercury. So this is vapor pressure of solution. Okay, thank you.